This is section 12.1, part C, performing a significance test for the slope. When the conditions for inference are met, we can use the slope b of the sample regression line to construct a confidence interval for the slope beta of the population regression line. We can also perform a significance test to determine whether a specified value of beta is plausible. The null hypothesis has the general form of h sub 0 beta is equal to the hypothesized value. To do a test, standardize b to get the test statistic. So we're going to do the test statistic equals the statistic minus the parameter all over the standard deviation of the statistic. Or t is equal to b minus beta sub 0 all over se sub b. To find the p-value, use the t distribution with n minus 2 degrees of freedom. Here are the details for the t-test for the slope. So suppose the conditions for inference are met. To test the hypothesis of h sub 0 beta equals the hypothesized value, you first need to calculate your test statistic, or your t-value. To do that, you're going to do b minus beta sub 0, and you're going to divide that by se sub b, or the standard error of the slope. Find the p-value by calculating the probability of getting t statistic this large or larger and the direction specified by the alternative hypothesis. And to do this, you are going to use the degrees of freedom of n minus 2. So if our hypothesized value is that beta is greater than our hypothesized, we are finding the area to the right. If it's less than, we're finding the area to the left. And if it's not equal to, remember that makes it a two-tailed test, and you're going to have to find the area on both sides. If sample data suggests a linear relationship between two variables, how can we determine whether this happens just by chance or whether there is actually a linear relationship between x and y in the population? By performing a test of h sub 0 of beta equals 0, the regression line with a slope of 0 is horizontal. That is, the mean of y does not change at all when x changes. So h sub 0 says that there is no linear relationship between x and y in the population. Put another way, h sub 0 says that the linear regression of y on x is of no value of predicting y. Regression output from the statistical software usually gives t and its two-sided p-value for the test of h sub 0 beta equals 0. For the one-sided test in the proper direction, just divide the p-value and the output by 2. So what this is basically saying is if you have a computer-generated information and they already tell you the t-value and the p-value is always going to be two-sided that they give you. But if your alternative hypothesis is one-sided, it's just less than or greater than, you're just going to take that p-value and divide it by 2. Infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Child development researchers explore the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. A snap of a rubber band on the sole of the foot caused the infants to cry. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the child's IQ at age 3 years old using the Stanford-Binet IQ test. The table below contains data from a random sample of 38 infants. So the first number tells you how many times they cried in the 20 active seconds, and then it tells you their later IQ score. So here's a scatter plot of the data for the least squares line with the least squares line added. Describe what this graph tells us about the relationship between the two variables. So if you're looking at the scatter plot, there is a moderately weak positive linear relationship between cry count and later IQ score, with no extreme outliers or potential influential observations. It appears that children who cry more vigorously tend to have higher IQs. What is the equation of the least squares regression line for predicting IQ at age 3 from the number of crying peaks, or the crying count? Define any variables that you use. So if we look at our coefficients, we can say our y hat is equal to our constant, which is 91.268, plus our slope times x. Or if you do that, you will have to define what your variables were. So in that case, y is going to be the predicted IQ score and x is the cry count. Or you can write your equation with the variables already defined in the equation. Interpret the slope of the y-intercept of the regression line in context. So the slope and the y-intercept. So when we're talking about the slope, for each additional cry peak in the most active 20 seconds, the regression line predicts an increase of about 1.5 IQ points. The y-intercept, the model predicts that an infant who doesn't cry when flicked with a rubber band will later have an IQ of about 91. Because there were no infants who recorded fewer than 9 cry peaks in their most active 20 seconds, it is a risky extrapolation to use this line to predict the value of y when x is equal to 0. We have no other data points that are close to it, so it's probably not going to be statistically significant in this case. Do these data provide convincing evidence that there is a positive linear relationship between the cry counts and IQ of the population of infants? Carry out an appropriate test to help answer this question. So we are going to have to do a 4-step problem. We're going to start with our state. So we want to perform a test of the null hypothesis as b equals 0 versus the alternative hypothesis that b is greater than 0, where beta is the true slope of the population regression line, relating crying counts to IQ scores. And since they do not give us a significance level, we're going to let alpha equal 0.05. Next is our plan. Remember, in the plan, you need to state what method you're going to use, and then you need to check your conditions. So if the conditions are met, we will do a t-test for the slope beta. Now, remember, we have a lot more conditions than we used to. So our first one is linear. The scatter plot suggests a moderately weak positive linear relationship between cry peaks and IQ. If we look at the residual plot, which is the second graph, it shows a random scatter of points about the residual equals 0 line. Next, we're going to look at independence. Later IQ scores of individual infants should be independent. Due to sampling without replacement, we do have to check that 10% condition, so we can assume there are 380 infants in the population from which these children were selected. Next is normal. The normal probability plot of the residuals, so if we look at the graph all the way to the right, shows a slight curvature, which suggests that the response may not be normally distributed about the line at each x value. With such a large sample, our sample is 38, however, the t procedures are robust against the departure from normality. Next is equal variance. The residual plot, which is the one in the middle, shows a fairly equal amount of scatter about the horizontal line. And last, we need to check random. We are told that there are 38 infants that were randomly selected. So since there's no obvious violations of the conditions, we can proceed with our inference. So next is the do part of our process. They give us a printout of the information. So the first thing we need to do is we can get the test statistic and the p-value from the Minitab output. If you look, we're not looking at the constant, we are looking at the cry count because the cry count is the one that's talking about the slope. We can calculate the t-value by doing our b minus our beta sub 0, which was 0. Sorry, we're going to do our slope over here, 1.4929 minus the 0 all over the standard error of the slope, and we get 3.07. Or if we just look over, it does give us our test statistic of 3.07. To get the p-value, if you were to do this by hand, you would need to do degrees of freedom there are 38 babies, so we're going to do n minus 2, which gives us 36. If we look at the Minitab output, it does give us a p-value of 0.004, but that's for a two-sided test. If you remember back to your hypothesis, we said that we were looking for a one-sided test, and our hypothesis was that beta was greater than 0. So to find our p-value for a one-sided test, we're just going to take our p-value and divide it by 2, and our p-value will be 0.002. So the last thing we need to do for this problem is to do our conclusion. The p-value of 0.002 is less than our alpha of 0.05. So we have enough evidence to reject the null hypothesis and conclude that there is a positive linear relationship between intensity of crying and IQ scores in the population of infants. Based on the results of the crying and IQ study, should we ask doctors and parents to make infants cry more so that they will be smarter later in life? That's hardly what we want them to do. This study gives statistically significant evidence of the positive relationship between the two variables. However, we cannot conclude that more intense crying as an infant causes an increase in IQ. Many infants who cry more are more alert to begin with and tend to score higher on intelligence tests. So this is our same printout that we had before. We know from previous chapters that confidence intervals give more information than tests do. Let's construct a 90% confidence interval for the slope beta in the crying and IQ example. The Minitab output from the linear regression analysis for these data give us that our B value is 1.4929 and the SE sub B is 0.4870. We need to find the critical value for T star for a 90% confidence interval from the T distribution. And remember, our degrees of freedom is 36 because there were 38 babies, and our degrees of freedom is n minus 2. Because table B does not have a degrees freedom 36 line, we are going to have to go to the next smallest degrees of freedom, so we will go to degrees of freedom of 30. You'll go across the line of degrees of freedom of 30 until we find the 90% confidence interval, and we will see that our T star value is going to be 1.697. Now, if you remember from the previous section, to find the confidence interval, we're going to do B plus or minus T star times SE sub B. Remember, we're going to do subtraction first and the addition second, and this is going to give us our interval. So we are 90% confident that the mean IQ increases roughly between 0.67 and 2.31 points for each additional peak in crying. Note that 0 is not included in this interval of plausible values for the parameter beta, which is consistent with us rejecting that null hypothesis in that previous example. Now, as a reminder from Chapter 3, your calculator can be used to find that least squares regression line. So what you would do is you'd enter your X values into list 1, your Y values into list 2. You're going to make sure that you hit mode, you go over down and check that your stat diagnostic is turned on. And then if you click on stat and go over to calc and select linear regression A plus BX, you need to make sure that your X list says L1 and your Y list says L2. If they don't, if you need to get list 1, you would just hit second and the number 1. If you need to get list 2, you'll hit second and the number 2. Then we're going to go ahead and store that regression line into our Y equals, so we'll graph it with our scatter plot. So to do this, you're going to go down where it says store reg equation. From there, you're going to hit the vars button. You're going to go over to Y vars, select function, then select Y1 and hit enter. If you go to graph the line and the scatter plot, then both will be visual. So you do need to make sure you hit second Y equals, make sure your stat plot 1 is turned on, make sure it is a scatter plot. And if you hit zoom and then select number 9, which is zoom stat, it will change your window so you can see both the scatter plot and the line. Once the least squares regression line is stored into your Y1, the residuals can be found and you can plot them. So if you go back to your list, you can define list 3 as the predicted values from the regression equation. So you'll go over, you'll highlight list 3, and you'll enter the command of Y1 parenthesis L1 and press enter. To get your Y1, you're just going to do the same thing you did before. You'll hit vars, go over to yvar, select function, and select Y1. This will tell you what you predict. So what is your predicted value for Y given your equation and the value for X? Now, if you remember, your residual is the observed minus expected. So residual equals observed minus expected. So on your calculator, if you go over and highlight list 4, now we can do list 2, which was our observed values, minus list 1, which is your expected values. If you do that where you have the name of it highlighted and hit enter, it'll calculate all of the residuals for you. Now, if we turn off plot 1 and the regression equation, we can specify that plot 2 will be list 1, which is our X values, and list 4, which will be our residuals. Again, we can use zoom stat, so you'd hit zoom, select number 9 to change the graph so that you can see the residual plot. If you need to plot the data itself, so to graph the probability plot, once the residuals are in list 4, you're going to turn off plots 1 and plot 2, and you're going to specify that plot 3 will be a probability plot. So if you go to the types of graphs when you're in the plot, it's going to be the last one. It's going to look almost like a scatter plot that's a straight line. And you're going to do this with list 4 for the data list. And if you hit zoom stat again, so zoom and select option 9, you will then have your probability plot.